talk about the sustainable HVAC design. Our agenda today will be a couple points. The first is the thermal comfort, controlling thermal comfort, fan and the fans and cooling effect, fans and destratification, application examples, and ancillary benefits. As, as Gallup mentioned, this presentation is accredited. So if anyone interested to continue the education and would like to get the certificate, we would be able to provide it right after the meeting. Quick heads up for the purpose and learning objects out of our presentation today. What we'll be learning today is we would identify the factor that affected the thermal comfort. We will understand what is the sustainability benefits of design strategy that use the air movement in conjunction with the traditional air conditioning systems. And we will describe how the elevated airspeed can improve the indoor air quality, as well identify the factor that affected the thermal comfort using the basis of ASHRAE standard 55. As well, we're gonna hit the understand how the ASHRAE standard 55 and 90.1 will be applied in a conditioned space. And last but not least, we will discuss how the air movement can assist with the meeting of the energy performance if we work and for requirements in a lead project. First, we would need to know what is the thermal comfort. So according to the ASHRAE 55, we have a definition for the thermal comfort. Definition is that the condition of mind which expresses satisfaction with the thermal environment and is assessed by subjective evaluation. Simply, thermal comfort is totally perspective from each one of us, for each one of us. Typically, if we are a group, 10 people in one meeting room or somewhere, and let's assume, for instance, we are between 22 to 25 degrees Celsius and RH about 50–55%. We would see majority of us feel comfort, but some of us will definitely not feel comfort. Some of them, they would be complaining, oh, it's a little bit chilly. Some others, they would complain, this is, oh, I feel a little bit hot. So most of the thermal comfort or the thermal comfort would be perspective from person to another person. That's mean probably the majority will be fine, but everyone has his own terms to identify the thermal comfort. So in reality, and that's what we mentioned, in reality, the thermal comfort is perspective, lag of noticing discomfort, and ability to focus on the work at the hand. Thermal comfort factors. There is some factors that affect our thermal comfort every day. There are actually 6 factors, 2 personal and 4 environmental. The 2 personal is closing insulation and metabolic rate. We definitely control what would be how many layers we wearing a day, and definitely we will control the action, which is generating the metabolic rate. And the four of them actually is environmental, which is the airspeed, air temperature, radiant temperature, and relative humidity. Closing insulation. Each layer we add in our body has a clue factor. The more layers you add in your body, more clue value. That means you feel much more warmer. Technically, every one of us during the winter time would be wearing multiple layers to keep themselves warm. Metabolic rate. Each one of us, each picture that we actually see, we will find someone who is standing, playing some guitar, versus someone who's biking, versus another one jogging. Each one of us had a metabolic rate based on the action. So the more action you do, the more metabolic rate you get, and the more warmer you feel. Air velocity. Air velocity influences flow from heat and from the body. Typically, every one of us during the summertime when you come to the office, come to the home, if there is no AC, the first thing you will definitely do that you want to turn on the fan at the maximum speed. Why? Because you feel hot, probably sweating. So the air flowing to your body, evaporating the moisture, and then you feel much more cooler. So impacts rate of the moisture evaporation from your skin. And that's we have another example that we have it daily, day to day, while we're driving the car at a high speed, probably 110 kilometer per hour. You feel much more during the summertime. Weather is like probably 30 degrees. You feel hot, and you just open the window, blowing all the air coming in, again crossing to your hand, your body, evaporate the moisture, and you feel much more cooler. Technically, temperature has not to change, but you get the perceived cooling coming out of the air speed coming through the window to your across to your body. And basically, this is where the science is. We see here the chart, the air speed at the horizontal axis versus the cooling effect at the vertical axis, and we will see if we have at any given point like at 300 feet per minute, we will see we would able to get roughly about 9 cooling effect Fahrenheit. And if we increase up to 700, you will see we can get up to 11. So if you increase over than 800, you would be able to get more cooling effect. So the more airspeed, the more cooling effect you can get. Bleeding mass. Here is a quick chart showing us predicted mean vote. Predicted mean vote, that's according to the ASHRAE 55, they have created a chart that showing at the thermal comfort zone, you will be in neutral, which we will see this smile face, which is around the 0. So at the 0, slightly above, slightly down, you are at the comfort zone. Moving forward to the right side, at the horizontal axis, you will be slightly warm and then warm, extremely hot. Moving to the left side at the horizontal axis, you will be slightly cool, and then cold. So we aim to be around the neutral. Here, the thermal comfort tool. Actually, the thermal comfort tool is available online. So you would be able to Google the thermal comfort tool by Berkeley University, and you would be able to have an access to the P psychometric chart, and you would be able to change the temperature that at the left hand side of the slide, operative temperature, airspeed, RH, metabolic, and the clothing level. As you start changing this parameter, it will move the point, the red dot in a shadow area. What we're trying to do today is we want to get allowance for the air movement. According to the ASHRAE 90, allows a credit for the airspeed. And today we're going to take an advantage of this credit, which is mean we equal thermal comfort must be maintained in the baseline. And definitely this is our aim to all of us to be to maintain the thermal comfort at any space, indoor space. That's actually optimizing the energy, and we will see a few cases how would the ceiling fan or taking a credit of the air movement in the space by the ceiling fan would able to optimize the energy in the space, and how we would able to earn a point based on the proposed building versus the baseline building energy cost. Heat transfer. We definitely all know the flow goes from the higher temperature to the lower temperature. We have a daily example for each one of us who drink coffee or tea every day. You got a hot coffee, a hot cup of tea in the morning. Roughly, the water is boiling at 100 degrees Celsius, so probably you have it in a cup around 90, and then you leave the cup and the table, which the atmosphere most likely would be roughly between 22 to 25 degrees Celsius. And if you start to be, get a couple of phone calls, and you find as if you check your cup of coffee later on, you will see that all the heat has been released and out of the tea or the coffee. And then if you come like 1 hour later or so, you will see it's become the liquid temperature equal to the surrounding temperature. And typically that's the heat transfer. So that occurs until the equilibrium is reached, and equilibrium that when the cooling equal to remove the heat. So releasing the heat until the liquid temperature will be equal to surrounding temperature. And there's 3 different modes of the heat transfer: convection, conduction, and radiation. I know probably 99% of all the audience, they aware of that, but it's a quick heads up for this basics. Radiation come from the heat, conduction come from the hand, and convection through the boiling water through the surrounding. We always say the human in a bad thermometer, because sometimes we really misjudge the situation or the surrounding. So, for example, if all of us in one room, and again, the room is 22 to 25 degrees, RH about 50%, most of us, again, will be convenient. But let's assume there's one coming out of sauna. It's about 80 degrees Celsius, 70 degrees Celsius, and he's stepping to a room which is between 22 to 25. He will definitely feel is a little bit cool, probably gonna feel cold. So even it's convenient for the majority of us, but still someone who's complaining and is actually misjudge the situation or the temperature. There is 3 different modes of the fan control. Typically, we use them during the year. So the first is increasing the airspeed to promote the received cooling. And typically, this is in the summertime. Every one of us feels hot. You're running the fan at the maximum speed because he wants to feel to cool down. In the winter time, you receive a lot of complaint for heat, that the heat is not reaching down the ground level. So we're running the fan at the low speed to promote the destratification. And overall, we can run the fan at the medium speed to have good mixing in the surrounding or the area. By elevating the airspeed, increases the convection cooling potential and evaporate the rates. And we have the Q convection equal to the height, multiply the area, multiply the temperature difference. Designing of cooling. Typically, the picture we see at the right-hand side of the slide that's showing us one of the projects we have helped to promote the cooling within a warehouse in some certain areas like shipping and receiving, workshop area where the employee is. So typically this is the area that most of the warehouses the actually looking for to get cooling for the workshop, for the employee, receiving, shipping and receiving area for the people they work. So we will see the blue area where the maximum air movement, high air movement in this area, where the area that's not covered by the fan will be in yellow color, red color. That will be yellow color will be less air movement, and red color that would be the dead zone. And typically you will see that at the corners and close to the walls, because that would be again, that will be the dead zone, and there is no air movement at these areas. So we have the Spec Lab, that the app that we usually use when we have our recommendation to do the design for a warehouse or hangar, office, whatever the application is, to provide the CFD, computational fluid dynamics, and it gives also the area metric, how much cooling effect you would able to get by running the fan at the 80% of the speed or 100% of the speed. Also gives information about destratification, how much percentage we would able to achieve the destratification within this area by using these numbers of fans, and that would be something able to provide to our customers. So only need the fan where the cooling is needed. That's typically what each one of us would really looking for. No mechanical cooling. That being said, that we are not, the ceiling fan is not at the AC, so we are not changing the temperature. So we just receive the perceived cooling effect coming off the air speed by spinning the fan at high speed. So no mechanical cooling, temperature does not change, only perceived temperature. We aim to get the highest and particular average airspeed. Very interesting case. Now we will see the thermal comfort with the traditional HVAC system, which is all of us aware of. So we got the space, had an air temperature design point at 23.8 degrees Celsius, RH 50%, air speed 0.5 meter per second. We are going to plug all the information or all the parameters that we actually have here at the B psychometric chart, and we will see where we are. So we will see the point at the left-hand side of the shadow area. The shadow area, it's simply at the thermal comfort. This is where each one of us wants to be within this area to feel the thermal comfort. So being at the point within the shadow area that I am in the thermal comfort. Wonderful. I will see the next slide. Now I'm going to add the ceiling fan to traditional HVAC system. But I'm going to go to the thermostat And I'm going to push the thermostat up from 23.8 to 26.1. And I'm going to run the fan to promote 0.6 meter per second, which is typically before was, in the previous case with the traditional HVAC system only was 0.15 meter per second. So I'm going to change the airspeed from 0.15, running the fan to promote 0.6 meter per second. And we're going to plug in the new data, 26.1, 0.6 meter per second, and the remaining parameters will remain the same. So the point has not changed. That means I am in a thermal comfort area in a B psychometric chart. So typically, I raised up the thermostat and still getting the same cooling effect and still getting the same thermal comfort area. Were they able to get to increase the were they able to increase the cooling in the space using the ceiling fan? Yes. And that will take us quickly back to the chart here. By increasing the airspeed, you would able to get a cooling effect. So you will see the point here. I'm going to rate the thermostat from 23.8 to 29.4, and I'm going to increase the airspeed from 0.15 to 0.6. And I'm still in shadow area, and the point has moved from the left-hand side to the right-hand side. So I'm still in the thermal comfort area and able to get increase the perceived cooling in the space. This is one of the school gym that we actually have done in Lexington, Kentucky. So we will see here, the location is about 7,833 square foot, and the set point is 22 degrees Celsius. We'll see the material and insulation cost $7.39 per square foot. If we apply the same concept to move up the thermostat from 22 to 25, that would able to save the material and insulation cost from $7.39 to $6.79. And this is definitely would has impact to material of the duct material, insulation, and the labor. And typically, if we see here, it's main duct in the middle, multiple branches with the exhaust to cover the entire area. Here, it's only one main duct and coupled ceiling fan with able to distribute and get the perceived cooling effect or air mixing in the space. So the material and installation cost, including the fan, would be 60 cents per square foot. Electricity, AC electricity consumption in the summertime would go down 38%. If we use the fan for this stratification during the winter, that would save roughly about 17%. And this is a picture from site that's showing us here the main duct and multiple branches. And here is how it looks like after we include the ceiling fan with the main duct in the middle. Again, it saves duct work, insulation, and labor cost as well. We got a very common question. Does the fan would be affected if the balls in the gym area would hit the fan? The question is no. Our fan has a number of safety redundancies and is very durable. It has a very durable design that if the ball hit, there is no damage would ever happen to the fan. And quickly, I'm gonna run the video for a couple seconds. Another, as I mentioned in a previous slide, our fans has been designed that it has plenty of safety features and redundancy that would be save the employee even if the forklift hit the fan. So I will quickly going to run the video and you will see what's going to happen if the forklift hit our fans, and I will explain where our safety features come from.
See for yourself. See for yourself.
So typically, our fans had the restraint airfoil system, that the strip that goes all the way through the airfoil that holding the airfoil from the hub all the way to the winglet. I will quickly move the slide a little bit forward, and that's exactly. So this is the strip is holding the airfoils all the way from the hub to the winglet that holding the airfoil. So as we saw actually in the video, if the forklift hit the airfoils will always remain attached to the fan. Another example for the offices the question is if we have a warehouse with able to get or a gym area able to get a perceived cooling, but do you think would be applicable in an office? Yes, it'd be applicable, and we have done that. And there's in a few slides we'll see one of example in offices. We have done same concept. We apply the same concept. And here is an example quickly we're going to go through, which is our design point is 25 degrees. Our design point is 23 degrees Celsius, and we'll see the material and installation cost that's including the duct, insulation, and the drop ceiling will cost us $5.61 per square foot. Now, we're going to read the thermostat from 23 to 25. You're going to get the same cooling effect, but your material and installation cost goes down from $5.61 to $2.46 per square foot. The fact is you saved the drop ceiling cost, you saved the duct, labor, and insulation. So typically here, this is the traditional HVAC system, and this picture shows us one main duct in the middle, a couple of fans with able to promote the cooling effect or air mixing or either destratification, and you get a saving. So our summary here: offset the thermostat by the cooling effect generated by the fan. In all the cases, we have set up the thermostat up 2 degrees, 3 degrees, and we still get the same cooling effect. And again, when we plugged all the numbers in the B psychrometric chart, we showing us we are in the thermal comfort area according to the H355. Running the cooling equipment less, absolutely yes, and reduce the energy and money saved. We totally understand, based on how big the area, the warehouse, the space, if we save 2 degrees, 3 degrees daily for running the HVAC equipment during the summertime, we would definitely understand how much saving we would able to get by the end of the season. Reduce the capex of the new builds, smaller cooling equipment. You can definitely consider the ceiling fan cooling effect, or the cooling effect comes out of the ceiling fan during the operation. And when you consider that, you would able to save the capital cost of the cooling equipment when you started the design for the HVAC system. Also reduce the OPEX, the operation cost during the time by the year. So typically by raising the thermostat up, you do some saving during the summer season. So additionally, comfort and productivity for all non-cooled space. Now we are going to talk about the stratification and what we call destratification. So basically, it's a main complaint comes out of most of the warehouses, hangars, manufacturing facility, especially with the high ceiling above 50 feet. They will always complain that up to the ceiling is too hot. If they have a mezzanine and goes up, always complaining this is too hot up to the ceiling, and mostly at the ground level, which is have the employee and the thermostat as well, is always cold, especially if we have gates opening on and off during the winter time. So, and here the second option, using the ceiling fan during the winter time. So this stratification, again, we aim to the ceiling height above the 15 feet or higher. Difficult to get uniform temperature, definitely. Without the ceiling fan, up high to the ceiling, it was always too hot. As we see in a picture, it's roughly about 88, 90 degrees Fahrenheit, and down is about 20 degrees Celsius or 68 degrees Fahrenheit. So we would like to get a typical destratification about 1 degrees Fahrenheit difference between the upper level and the ground level. Also depends on the building material, insulation, heating, equipment, and activity to set the point, and also the outdoor. So the multiple factors that affect this stratification within the warehouse, hangar, whatever the application we are working on. So how the building is, how the materials, insulation, and activity inside the building, what is the set point, and also what is the outdoor air temperature. We definitely looking forward to get the higher average space temperature and heat loss, and run the equipment less time. So it's always heat loss because thermostat is down at the ground level, which is permanently cold. And our point is we want to have this stratification and get the better mixing by running the fan at the low speed to let the thermostat identify the right temperature down at the ground level, and then the thermostat will, give a signal to the heater to stop. Otherwise, the heater will keep running all the time because the thermostat at the ground level read the cooling temperature only, not the right temperature. So, designing the destratification, the fans will be needed throughout the area that's served by the heat to achieve the maximum saving. And typically, if we see the picture at the right-hand side, we will see the air is circulated in the space. And what we're looking for is we want to mix the air in the space. And ideally, that's what we looking for. There's a guidelines and clearance we have to be maintained in order to ensure the circulation in the space. Typically 2 feet away from the airfoils, same fan diameter size below the fan, and also the distance between the roof deck and the airfoils. Also, we need to maintain vertically 3 foot from the airfoils up to the sprinkler system. That's according to the NFPA. However, again, we need the fans to be within the area that has the most of the heated air, and then we would just running the fan at the low speed to push all the warm air down and circulate the air in the space. We can have the fan apart from each other about 200 feet. We always say that the slow speed operation between 5 to 20% keep the airspeed below the pre-hold, which is roughly about 40 feet per minute. So typically below 40 feet per minute, there is no, you can't feel the air movement comes out of the ceiling fan. So you need to actually increase the airspeed above the 40 feet per minute. We do not need to reverse the fan in a winter time for this stratification. I guess it's a misconception for most of us that the fan needs to be run reversibly during the winter time. But we will see in the next slide, this is not recommended as a ceiling fan manufacturer, and that's due few reasons. The first is the airfoil design has an angle. As we see here, the fan has airfoil shape. So if you're running the fan reversibly, that's going to be against the fan, the airfoil design. So you wouldn't get the performance out of the fan. Additional load to the motor because you run the fan against the airfoil design. Insufficient air mixing. Typically, what we see the ground level, the people at the ground level where all the warm air is up. So if you're pushing all the air up, that means you really don't mix the air in the entire space. You just mix the air up high to the ceiling, which is mean less mixing down at the ground level, and typically the warm air will be up, and on top of that you are losing the heat by pushing all the heat to the roof deck. While in the picture at the left hand side is showing us the air is circulated, and you would able to get the benefit out of the ceiling fan by circulating the air in space. One of the example that was has been done for Kentucky National Guard. They had a problem with the stratification. They had 36 feet ceiling height, and they were able to solve the problem by using 24 fan diameter of the powerful X4. One of the certification study during the winter time, we got a reading at 3 different height of 5 feet, 15 feet, and 35 feet above the finished floor in 6-7 days from the day 2nd November all the way to day 10th. And we would record the temperature for each day at a different height level. And we will see the temperature will be at the 5 feet, it comes between 50 to 60. while above the 15 will be between 60 and 70, and 35 between 70 and 80. So that's while the fan is off. If we run the fan, we will see that the fan start working and mixing the air in the space. We will see the gap between the temperature for at a different ceiling height. We'll see the gap has been shrinkage, and we mostly have seen temperature probably 1 degree less between the 3 different level of height during the day. This is also would affect the gas consumption. So mostly if the fan is off, we will see the average temperature would be in the space 35.6 degrees Fahrenheit, while the average occupant level would be 56 degrees Fahrenheit, and the gas consumption would be 60,000. The gas consumption will be 60,000 cubic feet. While if the fan is on, that will mix the air in the space, and would be the average temperature goes up from 35.6 to 35.8, and we'll see 0.2 degrees average temperature when we mix the air by using the fan, and the average occupant level goes to 56.7 with 0.6 temperature difference, and the gas consumption goes down to 49, almost to 49,000 cubic feet. That's will show us the difference is about 10,000 or 10,983 cubic feet. If we have more than 0.2, if we move up the difference temperature from 0.2 to 2.1 average temperature in the space, while the at occupant level will be 0.4, that's going to, we will see a gas consumption difference goes to 14,951. So that's mean by we will see that the difference temperature at 0.2 that has impact about 11,000 cubic feet gas usage. We see the case at the 2.1 degrees Fahrenheit difference, we'll see about 15,000 cubic feet. So the result out of the study is the annualized gas saving would be 272,247 cubic feet. The cost saving would goes to 2,714, while the fan operation will be $37. So simply if we do the math, we will see we're able to get a net saving about 2,677. And we have done the calculation for the heat saving, how much heat saving you would able, how much money you would able to save by the end of the year by using the ceiling fan. So this is something we would able to provide if you are interested to see how much is saving if you would like to combine the ceiling fan for destratification with the heaters during the winter time. We have the destratification study here for one of our project in Cassidy Elementary School. They had an issue with the destratification, and then the ceiling height is 33 feet height, and the heater is running non-stop. So using the fan to achieve destratification, roughly about 2 10-feet fan diameter essence fan would able to achieve the destratification. Here is another chart showing us destratification the first week of the library. As we see, the temperature has at the different the temperature at different heights from 4 feet all the way up to 18 feet. We will see the temperature has a different at the different height we see the different temperature is, while when the fan on, the curve is mostly looks like a flat. So the result out of the case is overall 16.3% decreases in the HVAC during the summertime, for the heating during the running the ceiling fan. This stratification will be reduced from roughly about 4.3 degrees Fahrenheit to 1 degrees at 18 ceiling level height, and the background noise level would be roughly about 1.7 dBA, which is roughly about 4.5%. This is one of the picture for our R&D facility based on Lexington, Kentucky, where we have our headquarters and our R&D facility. So if basically we would like to have the fan in a classroom, we run the fan and we in a multiple speed, we will see at which speed the fan the documents or the paper will last in the desktop, and at which speed the paper will start flying away. So that means that all our products would be tested in our R&D facility before we release it to our customer. That's one of the application we have done in Quebec office in Oakville, Ontario, Canada. They have a design firm. That the design firm was Red Studio. The issue was air distribution, this stratification. We have solved the problem by 17 high volume speed fan. It was warehouses and the offices as well. So the result is coverage 100%, reduce the HVAC tonnage roughly about 90%, and raise the set point for going saving as well, reduce the light grid and the size. So basically all our fan has an option to come with the LED light kit, starting from the residential fan, commercial fan, all the way to the industrial fan as well. British Airways, one of the cases that they had an issue with the destratification. They have an issue for 11 degrees Celsius temperature difference between the catwalk and the ground level workers. And what we see here, 524 ceiling fan for the hangar would able to save $114,000 by lowering the consumption to 2 million kilowatt hour. If any one of us has been in Dominican Republic, especially in Punta Cana International Airport, you will see our powerful 8 fans has been installed. 38 of them was able to provide roughly about 6 degrees perceived cooling in the Caribbean heat, allows the airport to retain charm and increase the overall flow and comfort. As we all know, the airport actually has open areas, like the doors is always open, and weather is really hot, especially during the summertime. One of other application in Bill's nursery. So they have the issue is excessive moisture and causing plant diseases and fungus. 10% losses on 100 million plant growing per year. How we would able to solve the problem by using high volume low speed fan, 24 foot, about 3 of them, that would able to distribute the airflow throughout the racks and evaporating the moisture, and 70% decrease in a product loss and eliminate the wasted the floor space for pedestal fans. The comfort, this is a quick chart showing us the comfort versus the productivity. Typically, we will see if we don't really being in a thermal comfort, we would be able to be productive. Typically, each one of us, if he comes to the office in the morning, or an employee go to the manufacturer facility, if it's too cold, if it's too hot, if you go to the office, AVC doesn't work during the summertime, or the heater is not working during the winter time, each one of us will start complain and would able to provide being productive and do the work. So that's chart showing us in a multiple different temperature how would be the productivity loss. That's one of the example for has been done in Kentucky for a manufacturer facility has 25 employees. Each one has an average wage, hourly wage about $15 for 40 hours. We'll see the money lost for less productivity about $15,000. Big S fans would able to save up to $9,000 per year. That's increased the productivity up to 60%. There is last two examples to show us how to improve the indoor air quality. One of them, the when we have the fans in a swimming pool, we all know that all the swimming pool had a harsh chemical, and most of this harsh chemical running on the top of the surface, and each one of us in the swimming pool will inhale the air mixed with the harsh chemical. So how would be the ceiling fan improve the indoor air quality? So typically what we're trying to do is running the fan at a certain speed that's increase the airflow over the surface, pushing all the air towards the exhaust and bring more fresh air out of the duct. So typically what we try to do, we try to eliminate the amount of the harsh chemical that's running in top of the surface. Another example that the manufacturer facility, the steel manufacturer facility, which is condensation medication, we all know the moist and cool surface create condensation, and that actually leads to corrosion. And corrosion mean typically material loss. So what we try to do is running the fan at a certain speed to increase the overflow and air speed over the surface, evaporate all the moist, and then it eliminate the corrosion. So elevated air speed over the condensation promote evaporation and increase the temperature near the floor. Last slide actually showing us the comes to the design when you have, if you're looking for roughly about 600 CFM within a space. So typically you were looking for 750 CFM using the ease factor 0.1. So typically by using the fan, you would use the ease factor around 1 because the ceiling fan would be able to circulate the air in the space without being add an additional air in the space. So strategically placed at the HVLS fan forces the effectiveness to be around 1. Conclusion, as we are trying to shift the concept of the thermal comfort, we will see in US 6% generated by the electricity of using the AC that cost them roughly about $29 billion for the EC only. And using the EC, that's mean carbon and emissions. So that's about 117 million metric tons of carbon. 63% of the rises of the cost of the electricity since 2003. What we're looking for now is building the design is more green focused and try to eliminate the emissions and lowering the cost. Additionally, for when we start the design for the material and the equipment, plus the running cost by setting the thermostat up. We will all just have a quick question: what if a home in each home in US raised the temperature roughly about 6 degrees Fahrenheit? We will see visible with the elevated airspeed, while creating cooling effect that would able to eliminate to 35 million metric tons of carbon and emissions. By now, I guess my presentation has done, and yeah, if there's any question, I will be more than happy to answer.
Thank you, Mohammed, for this presentation and the valuable information you shared, especially that video. Now I'm tempted to go try to hit one of the fans with the ball. We do have some questions here in the chat area. If you guys have any questions, please add it in the chat area. First question here I have is, does the fans vary speed based on space conditions, or are they or do they have like a set speed from factory or programmed speed?
So typically, our fans has an option to come with the Bobcon control. Bobcon control is a touch screen smart controller that has a temperature sensor. So you would able to set the fan at a certain speed, and the fan will be running automatically based on the temperature that you actually set the fan or set the thermostat on. This is one of the options. And the second option is you would able to run the fan through the automation system. If you are looking forward to run the fan out of the from the automation system they actually have in the building. So if you're looking for cooling, you're gonna definitely running the fan at the high speed. If you're looking for this stratification, there will be site setting. There will be something based on, again, the material, the activity in the space. So you would able to set that based on, it will be condition, will be different from space to another space based on the condition for each facility.
Okay, it's good. I don't see any other questions other than they're asking for selections. I ask everyone that has any questions or want selections to contact your closest Odell office, and we'll be able to help you along with Big Ass Fans. I guess this concludes our session here. Actually, I do have a couple of questions. No.
Sure.
Here, Alpha gives you. No, I guess that's it.
Okay.
Thank you guys, everyone, and hopefully we'll see you in the next webinar. Thank you.
Thank you very much. Thank you, Lil, for having me. Thank you, everyone. Take care.